All right, welcome back to Real Analysis. Continuing our work in Chapter 7 on the derivative in Section 7.5, we're going to take a look at a notion called local extrema. We've already seen in the extreme value theorem that a continuous function on a closed interval has absolute extrema, global extrema. And in this section, we're going to look at a familiar idea from calculus that the derivative is involved in locating not global extrema, but local extrema in the case that the function is differentiable. Right, so we'll start with some terminology. I'm going to kind of go over this quickly because I'm assuming you're sort of familiar with the calculus. This is really just to establish our notation. But kind of the preamble stuff, we have some function defined on a subset of the real numbers. So define the domain to be called A. The function f is defined on this set A. So we're going to call the number A. I'm not insisting on A being an interval here. So X may or may not be an accumulation point. But in any case, I'm going to call it a local minimum for f. So that's the term I'm defining. I've kind of bolded it in blue here. So the local minimum is an element of the domain. And it's a local minimum if there's some neighborhood, some epsilon neighborhood of that point. So that if you take any valid input, that is any x that belongs to that neighborhood and the domain, that the value at that x naught would be less than or equal to the value of any other x. All right, so it's a minimum in the sense that it's got an output value less than or equal to other output values, but it's local in the sense that that's only true in some neighborhood, right? There's some neighborhood around x naught for which the other valid inputs always have outputs that are at least as big. Nice. Okay, so I won't spend a lot of time talking about the kind of flip side of this, a local maximum. Same thing, it's a point in the domain. So x naught is a local maximum if there's some epsilon neighborhood where the value there is greater than or equal to all other values. Okay, so again, it's a maximum in the sense that it has an output that's greater than or equal to other outputs, but it's local in the sense that it's only happening in some neighborhood. Okay, so if you want to specify that it's one or of those things, but without saying which kind, we use this word extremum. So a local extremum is either a local minimum or a local maximum. So typical terminology from calculus. Here I've kind of clipped a picture from our Math 109 text here at HSU. So it just kind of illustrates this function. This function has a local maximum at the input x equals c. So if you look at that input x equals c, there's some neighborhood, you can visualize it. It's not just one, but at least there exists one. There's some epsilon neighborhood of c, so that if you only look at the outputs on the part of the graph that are around in that where the inputs are coming from that neighborhood, then the value of f of c is bigger than or equal to those other outputs. Okay, likewise, you can see that there's a local minimum at this point called D. Same kind of idea. There's some neighborhood. It's not unique, but there's some neighborhood around D that if you only look at the outputs of points in that neighborhood, f of D is less than or equal to all of those things. I like this picture because it illustrates that, this function, if we kind of extrapolate off to the sides of the picture, it's not a bounded function. So it doesn't have any absolute extrema, doesn't have an absolute minimum because it looks like this arrow means that the values will just descend indefinitely. It doesn't have an absolute maximum because they ascend indefinitely. So functions can have these local extrema without having global extrema. They might have, every global extrema is certainly local, right? If you're literally the biggest output on the graph, well, then you're in particular the biggest output in some neighborhood, but not vice versa, right? You can have this function's outputs could get bigger than f of c, they just do so quote unquote far away from c. Cool. So the theorem that we want to prove in this section, this is the version stated in our calculus text here at HSU. It's attributed to Fairmont. I'm not actually familiar with the actual history here, but our calculus text calls it Fairmont's theorem. And it says that if you're having a local extrema, a max or min at some point C, and if you're differentiable at that point C, then the derivative has to vanish at that point C. And the derivative has to have the value 0, as indicated in this picture. Yeah, if we're kind of thinking about the derivative as being the slope of a tangent line, we haven't really emphasized that much in this course, but it's certainly familiar from calculus. Notice that at both of those local extrema, it certainly is the case that the derivative is equal to 0 there. The tangent lines are horizontal. All right, so what's the number and how does this look in our book? Well, the statement of it in our book is the following. So here we are going to specialize off to the case of an interval. So that we can use limit language. Every point in an interval is an accumulation point. So the preamble in the theorem is you've got some interval I, you got a function defined on it, and let's suppose that this function has a local extrema at I. So I'm not specializing into which kind. I'm going to prove this for the case of a minimum and leave the corresponding case of maximum to you. I think it's also written in your text, but I won't prove both. But the theorem says if you have a local extrema, and very important part of the hypothesis, the function is differentiable at that point, well, then the derivative has to equal 0 at that point. Okay, so if you're a local min or a local max at a point of differentiability, the derivative has to take the value 0. So let's just proceed with the argument here. So let's use the statement of the notation to, of the theorem rather, to establish a notation. So we won't repeat everything, but let's suppose that this function f has a local minimum at I, okay? So I'm gonna specialize off into that case, leaving the case of local maximum to you. It's written in your text, but before you look at it, maybe, or you've probably already looked at it, but maybe you could try to just modify this proof, see where you could make the right changes to adopt this proof into the case of a local maximum. Okay, so I'm assuming I've got a local minimum at this point x naught in my interval, and I'm assuming that f prime exists at that point x naught. Okay, so by definition of what? By definition of local minimum, there's some epsilon neighborhood so that this function at x naught, its value is less than or equal to any other value, well, at least in neighborhoods that's in some neighborhood of that point x naught. So the only reason I'm intersecting that neighborhood with I here is so that it makes sense to plug things in, because that neighborhood might have points in it that aren't in I. So I just look at the ones in the domain. Okay, so I've kind of drawn that neighborhood over here on the left of the screen. And in particular, just for a second here, I'm going to focus on points in that neighborhood that are bigger than or equal to x naught. So I've colored it in red. Okay, so I'm looking at any x, because it's true for any x in the entire neighborhood. So in particular, if x is bigger than x naught, but less than x naught plus epsilon, so it's in the sort of quote unquote right half of this epsilon neighborhood. And again, it's a point in I. Well, because x is bigger than x naught, that difference is positive, right? We've already said that f of x naught is less than or equal to f of x, so this difference is also greater than or equal to 0. So the ratio is greater than or equal to 0. Ratio of two numbers, both of which are greater than or equal to 0, is greater than or equal to 0. The denominator, of course, cannot equal 0. Okay? So then if that's true, if I take a limit, technically speaking, I should use kind of the restriction of f to this right-hand side. We didn't formally develop this, but some of you guys use this notation. I'm just taking a limit, letting x approach x naught from the right, quote unquote. So from points in that red interval. So that's kind of another way to think about what I'm doing here is I'm saying I'm just going to let x approach x naught, but I'm only doing it from values that are bigger than x naught. And we have a limit law, it's 519, that says, well, if every one of these outputs is greater than or equal to 0, so is the limit. Okay, so what have I proven? I've proven that f prime of x naught is greater than or equal to 0. But now I'm just going to kind of flip the argument over. If we only took x's that were not on the right-hand side of that neighborhood, but on the left, I've drawn it in blue here. So I'm picking x's that are between x minus epsilon and x naught. Well, then the difference x minus x naught is always negative. The function outputs is still greater than or equal to 0. F of x naught is still a minimum. But if you take a number that's greater than or equal to 0 and you divide it by something that's less than 0, the ratio will be less than or equal to 0. Okay, so same kind of idea. If I let x approach x naught only from values that are less than it, that's a so-called left-hand limit. Uh, and that same limit law says that, well, if all of those function outputs are less than or equal to zero, so is the limit. Okay, so what have we done? We have simultaneously shown that f of x naught is less than or equal to zero, but we also showed that it's greater than or equal to zero. Well, the only number that can satisfy both of those inequalities is zero. So this derivative has to be zero. Okay. So you can modify the proof to show the same thing in the case that x0 is a local maximum. Nice. Okay. Um, the converse of that theorem is false. So the theorem says that, at a point where something's differentiable, if you're in extrema, the derivative is zero, but it doesn't say only if. So you've probably seen this example in a calculus course. It's kind of the nicest one to write down quickly. But if you look at the cubing function, well, our power rule says its derivative is 3x squared. That's certainly going to be zero at zero, but there's no local extrema at x equals zero. If I make kind of a little hand sketch of the cubing function here, a crude graph, I can see that the derivative is zero there, but in any neighborhood of the origin, f of zero is neither a minimum nor a maximum. Okay, so it's not a characterization of local extrema. It just gives you a place to look for them. Cool. So we're going to end by kind of just stating a corollary and having a little brief conversation here that if we take some function on a closed interval, right, and you take x0 to be an absolute extremum for it, I know such a thing exists by the extreme value theorem. Well, then there's one of three things that has to be true about that x0. Because if it's an absolute extremum, well, either it could be a local extremum, and if the function is differentiable there, we just proved that the derivative would have to be zero. Okay, it's possible that the function's just not even differentiable there, or it's possible that one of the points is an endpoint of the interval, in which case there's no sort of open interval around it to be a local extrema, because it could literally not be defined for x less than a or x less than b. So in calculus courses, we usually call inputs x0 critical values of the function if one of these two first conditions hold. Yeah. So a critical value of a function in a calculus class is by definition a number for which the function's derivative is zero or the function's derivative is undefined. So you learned this procedure in calculus to optimize functions on closed intervals. You made a table of its critical values together with the two endpoints, and then you just kind of looked in your calculus class. There was typically a finite number of rows in that table. In fact, the examples in calculus were carefully chosen to make sure that's true. So that's probably a familiar thing. If you took calculus here at HSU and you still have your book, you can look. It's the first section of chapter 4 is where all of this stuff gets discussed. Okay, so these critical points, things in the above corollary of type 1 and 2, usually in calculus courses there were just a finite number of them. So the set of these critical points was finite. But in general, things can be much more complicated. Okay, so we won't include the details here and really in the lecture in the Zoom meetings either. But if you're interested in such things, the section 7.5 exercises illustrate some examples in which functions have, well, more critical points than you might be used to. Okay, I'm going to ask you to think about one such function, but not kind of in the detail level of a typical homework assignment, but rather just sort of in a conversational way in your reflection. Okay, so we're going to end the video there. Thanks for listening.